Assalamu alaikum dear students. I welcome you to 29th lecture of probability and stochastic processes. In previous lecture we were investigating the relationship between the underlying random variables and transformed random variables in terms of the mean, variance and other moments. We were trying to find if it is possible to find the mean and variance of a pair of transformed random variables from mean and variance of a pair of underlying random variables without finding the joint PDF of derived random variables. And we found that yes, it is possible. And if the transformation is linear, the relationship is very nice in a sense that the mean values of pair of transformed random variables is the same transformation that we use to transform random variables, and we just take the mean values of underlying random variables, transform it with the transformation matrix we used to define a pair of derived random variables in terms of a pair of underlying random variables, and the result of this transformation is the mean values of the pair of derived random variables. Similarly, if we knew the variances of two underlying random variables, we can find the variances of two transformed random variables through a quadratic form. And for that, we need not only variances but the covariance also. So if you know the variances of two underlying random variables and their covariance, you can use that and the transformation matrix to find the variance and covariance of pair of transformed random variables. And under this linear transformation, we saw that it is quite possible that underlying random variables are uncorrelated, but the pair of derived random variables have some correlation between them. And we also were trying to find such transformations that took a pair of correlated random variables and gave us a pair of uncorrelated transformed random variables. And we were trying to design such linear transformations through the usage of eigenvectors and eigenvalues. For a square n by n invertible matrix, there is a special column vector that when you transform this column vector through multiplication of this square matrix and the column vector, the result is a new column vector. But it is such a transformation that the transformed column vector is just a scaled multiple of original column vector. The scaling factor could be positive or negative. If such a relationship exists, then the column vector which gets transformed to become a scaled version of itself is called eigenvector, and the scaling factor is called eigenvalue. In last lecture, we were working with a 2 by 2 square matrix and its two eigenvectors. Let's continue with the exploration of relationship between eigenvalues and eigenvectors and how we can use these relationships to design special linear transformations so that a pair of correlated random variables become a pair of uncorrelated random variables. So as you can see, if we have a transformation matrix T, then we have two special eigenvectors A1 and A2 and corresponding eigenvalues lambda 1 and lambda 2. The relationship is such that transformation of A1 is lambda 1 times A1 and transformation of A2 gives us lambda 2 times A2. We can represent this transformation and this transformation in a special matrix multiplication. I have written A1 here with its x component above and its y component below, and I have written A2 here with its x component above and y component below. So if this transformation matrix works on this column, then the result is lambda 1 times this thing. So when multiplication result should be seen, there should be lambda 1 here and lambda 1 here. Similarly, when this transformation matrix works on this column vector, then the result should be lambda 2 times this column vector. So we should see a lambda 2 here and a lambda 2 here. I have put the same column vectors here and here. This is column vector A1 and this is column vector A2. And this is a special diagonal matrix having lambda 1 and lambda 2 here and 0 here. We have to put this matrix here and this matrix here, and the result is when you multiply this, then this gets multiplied with lambda 1 and this also gets multiplied with lambda 1. So result is that you see lambda 1 here and lambda 2 here and here. So this multiplication of two matrices here and two matrices here, with this matrix being a special diagonal matrix containing the two eigenvalues, represents these two transformations. If we can use symbols T for this transformation matrix and A for this square matrix, which is a column vector here which is the first eigenvector and a column vector here which is second eigenvector, then this whole equation is transformation of this square matrix A is equal to multiplication of this square matrix A times this capital gamma representing this diagonal matrix with lambda 1 here and lambda 2 here and zeros in the off diagonal locations. If we want to have just this diagonal matrix on one side of this equality, we have to use inverse of this matrix and pre-multiply both sides of this equation with that inverse, and then we'll have this equation. This equation is obtained by pre-multiplying this equation on both sides with inverse of A. When you put inverse of A here, it becomes A inverse times A, and on this side there is A inverse times A, which is identity. You can remove that, and the result is that this diagonal matrix capital lambda becomes equal to A inverse times A. This equation is very similar to the quadratic form that we saw when we transformed the covariance matrix of underlying random variables with a linear transformation to get the covariance matrix of the transformed pair of random variables. But in that case, the two outside matrices were transpose of each other. We were having an equation where it was A transpose times kxy times A. But here we have A inverse and then T and then A. Fortunately, for the matrices which are formed with eigenvectors as columns, if these eigenvectors are unit norm, if the length in the sense of Euclidean length, where Euclidean length is square root of sum of squares of all these elements, if the length, Euclidean length of this column vector and this column vector is 1, then inverse of this matrix is just its transpose. So if that condition is satisfied, that this matrix has unit norm column vectors, then this equation becomes A transpose T A equal to lambda. So if we have a transformation matrix T and we know its eigenvalues and eigenvectors, and we take eigenvectors and put them as column vectors and get a square matrix A, and we take care of the lengths of these column vectors and make sure they are all 1, then its transpose is its inverse, and based on this pre-multiplication of A inverse, we get this relationship, which is again a quadratic form. A transpose T A is equal to capital lambda, which is this matrix, which is a diagonal matrix, has only entries in this principal axis, and the entries on the off diagonal locations are 0. I hope you can see the connection here. In transformation of a pair of random variables to a pair of derived random variables, we transformed this through a linear transformation and saw that the covariance matrix of pair of underlying random variables becomes a new matrix, where new matrix is a quadratic form. So if the underlying random variables were uncorrelated, then it is possible that the pair of derived random variables were correlated. But if the pair of underlying random variables were correlated, we wanted to find a transformation which, when applied to the pair of underlying random variables, gave us a pair of transformed random variables which were uncorrelated, which had a covariance matrix with only entries present on the principal axis and off-diagonal elements being 0. So let's suppose you start with a pair of underlying random variables x and y, and they are correlated. You find their covariance matrix, which is a 2 by 2 matrix with top left entry being the variance of the first random variable, bottom right entry being the variance of second random variable, and off diagonal entries are same and they are covariance between the two random variables. Now you want to design a linear transformation so that you get a pair of derived random variables u and v, and you find the covariance matrix of u and v, capital K u v, and this capital K u v should have a property that its off diagonal elements should be 0 or it should be a diagonal matrix. You can achieve that by following the procedure we just outlined. In that procedure, we started with a transformation matrix T. We found its eigenvectors. We put the eigenvectors as column vectors of a square matrix and called that A. We made sure that all the column vectors had unit length, and then we took its transpose, and then we formed a quadratic form A transpose times T times A, and that came out to be equal to a diagonal matrix which consisted of eigenvalues of the transformation matrix T. Now we are starting with covariance matrix of underlying random variables x and y, and this covariance matrix is not diagonal. It has some covariance values. So if it has non-zero covariance values, then off diagonal elements are not 0. So you start with that, and you want to transform it through a quadratic form into a matrix K u v, which is diagonal. Remember that the transformation, the linear transformation which transforms x and y to u and v, is the one we use in the quadratic form which transforms the covariance of x and y into covariance matrix of u and v. So the same type of quadratic form that we saw previously can be used. So this kxy, the covariance matrix of underlying random variables x and y, serves as capital T in the procedure we outlined. So we will find the eigenvectors and eigenvalues of this kxy, the covariance matrix, and only condition this covariance matrix must satisfy is that it should be invertible. So if this covariance matrix of x and y is invertible, you find the eigenvectors of this covariance matrix, and then you normalize all those eigenvectors such that their lengths are 1. And then you put those column vectors in a square matrix, and that is your linear transformation that you can use to transform a pair of correlated random variables x and y, and through this linear transformation you will get a pair of uncorrelated random variables u and v. This procedure is called diagonalization of a matrix. We started with the covariance matrix of x and y, and this covariance matrix was not diagonal. We used a quadratic form to transform this covariance matrix into a new covariance matrix of transformed random variables, and this covariance matrix of transformed random variables was diagonal. This procedure can be used if we have a pair of correlated random variables to find a linear transformation which will transform the pair of correlated random variables to a pair of uncorrelated random variables. Now suppose you start with a pair of uncorrelated random variables x and y, and you use a transformation, a linear or perhaps a non-linear one, to get a pair of transformed random variables u and v, and they are correlated. Now, can we find a linear transformation which transforms this correlated u and v back to uncorrelated x and y? The answer is, if the original transformation which took uncorrelated x and y and gave correlated u and v, if that transformation was linear, you can certainly find the reverse transformation which takes u and v, the pair of correlated random variables, and you can get your original x and y which are uncorrelated. But if you transform x and y into u and v through a non-linear transformation, then if you design your linear transformation which takes this pair of u and v which are uncorrelated to get a pair of uncorrelated random variables, you may not get the original x and y. You will start with u and v, pair of correlated random variable, and if they were obtained through a non-linear transformation, then the linear transformation which takes this correlated u and v and gives you a pair of new random variables which are uncorrelated, then this transformation may not give you your original x and y. They will be two new random variables. But you can always get a pair of uncorrelated random variables. They may not be the original uncorrelated pair of random variables you started with, but that's not the aim. The aim is that you start with a pair of correlated random variables, you find their covariance matrix, use the eigenvectors of that covariance matrix to design a linear transformation to get from that pair of correlated random variables to a new transformed pair of random variables which are uncorrelated. This procedure has many applications in pattern recognition and other applied areas where the transformation is designed in such a way that correlated random variables become, after transformation, uncorrelated. With this discussion of transformation of a pair of correlated random variables to a pair of uncorrelated random variables through a linear transformation, we conclude our discussion of a pair of random variables. In this discussion, we covered the joint PDF of two random variables, transformation of two random variables to a new pair of random variables, the relationship between the joint PDF of underlying pair and the joint PDF of transformed pair, and the relationship between means and variances of underlying pair of random variables with means and variances of transformed random variable pair. There are certain situations where we need more than two random variables. A few lectures ago, we discussed an example where we said that if you go to a university and pick a student randomly and measure his or her height, his or her weight, or any other parameter, then you are measuring an unpredictable quantity. If you pick a student randomly, then the height of that student is a random variable. You cannot predict what the height of the next randomly picked student will be. Similarly, weight is also an unpredictable measurement. But there are situations where you need to measure more than just height and weight. For example, if you want to screen a certain population, say students in a university, for possible heart attack risk in future, you would like to measure not only the weight, but the cholesterol level, the family history, that is, how many members, how many ancestors have died of heart attack. When we are talking about cholesterol level, you have to measure both the good cholesterol and the bad cholesterol. There are two types, and you have to take into account if the person smokes or does not smoke. That's also an unpredictable quantity which can take on value of yes or no, 0 or 1. There are other risk factors involved, the lifestyle, the pollution, where the person lives, etc., etc. So to make a decision about the possible risk of a future heart attack, you have to measure or observe or find more than two unpredictable, unforecastable quantities. And you can arrange all these observations, those measurements, in a vector form, and then you are dealing with a vector of random variables. More than two, possibly 5, 10, 15 or even more. So there are situations where you need to make observations which are more than two, and then you are dealing with a collection of random variables, a vector of random variables with length 3, 5, 10, 20 or whatever. There are other situations in applied sciences, in computer science, in electrical engineering, where we need to work with more than two unpredictable observations. For example, you have designed a character recognition system. You have placed a camera, a computer, and the camera takes the image of an unknown character, and this image goes inside the computer, and then computer makes some calculations on that image. Since this image is unpredictable to the computer, computer does not know beforehand which image is going to be placed in front of camera. This is an unpredictable experiment. So when a new image is displayed in front of the camera captures the image goes inside the computer, and then the resident software analyzes such an image. Here is an example of such an image. You can certainly recognize this as Urdu alphabet wow, but when this image goes inside the computer has to make some measurements on this image. For example, it can measure the extent of the image, the horizontal extent or the vertical extent, the minimum and maximum rows, the difference of maximum row and minimum row between which the character lies. Similarly, the minimum column and the maximum column between which the character lies, this image lies. The computer can find other quantities which are unpredictable, which computer did not know before this image was shown, and one of these quantity will be the boundary length. The computer can measure the boundary length of this image, and it can measure the centroid. Centroid is a point on x and y axis in such a way that the signed distance to all the pixels when summed up becomes 0. The computer can measure other higher moments. Computer can find the projection. In projection, you take a vertical line and then you count number of pixels, black pixels on each row. So if in this row there are 7 pixels, you put 7 here. If there are more pixels on the bottom rows, you have higher numbers, and this profile, which is called projection, which will be a low value here, a high value here, and a high value here, is a projection on vertical line. You can have a projection on horizontal line, where this projection will have a lot of value and projection along these columns will have small values. So the pattern recognition software in the computer makes many observations on the image it sees in front of the camera, and based on these observations it can decide if this character is a waw, an alif or be or some other character of Urdu language. So when you have more than two unpredictable observations, you do not want to mix the observations. So each observation has its own specific location in the scheme of things. So you make a vector. You don't make a set of observations, you always make a vector of observation so that each observation has its own proper location. So when you are dealing with a vector of observations, you say that this vector valued observation vector comes from a vector of random variables, and you denote such a vector of random variable with capital letters like A, B, C, X. Suppose you have observations coming to you and each observation is coming from different random variables x1, x2, x3 all the way to xn. You form a vector of length n from these random variables x1 to xn and you denote it with capital X. So capital X is equal to a vector which has entries x1, x2, x3 all the way to xn, and a vector valued observation is denoted with small letters. So small letter x is also a vector and it has specific values of different random variables. So you can say a random vector x assumes a value which is also a random vector of the same length. With this notation, you can go ahead and find the joint PDF of a random vector, a joint CDF of random vector, and other quantities of interest. A joint PDF of a random vector of length capital N is a function from Rn n-dimensional space to R1. So it's a field. The argument is an n-dimensional vector, n quantities, and the result is just a scalar. So this joint PDF of a random vector of length n is a function from Rn nth dimensional real valued space to R1. Similarly, a joint CDF of random vector of length n is a function from capital R raised to power n n-dimensional real space to R1 with a further restriction that the maximum value that this joint CDF can attain is 1, and this value of 1 is attained when all the values, all elements approach plus infinity. If you have a joint CDF of a random vector, you can certainly find joint PDF of random vector by taking partial derivatives with respect to all the elements in the random vector. Similarly, if you have a joint PDF of a random vector, you can find the joint CDF by taking parameterized integration of joint PDF with respect to all the elements in the joint vector. If you have joint PDF of a random vector, you can find all sorts of marginal densities from that joint PDF. You can certainly find the marginal densities for all individual random variables in that random vector, but you can also find joint densities of two random variables in that random vector. You can pick any two random variables in the vector and you can find the joint PDF of that pair of random variables. You can find joint PDF of any vector of lower dimension than the dimension of the given random vector. So if you are starting with a random vector of length 10, you can pick any 3, 4, 5 or any number up to 9 individual random variables and find the joint density of that lower dimension random vector. You do that through integration. If you want to find the marginal PDF of first element in a random vector, you take the joint PDF and integrate it with respect to all other parameters, the second, third, up to 10th. And if you want to find the joint PDF of second and fifth random variables in a random vector, you integrate the joint PDF with respect to all other parameters, the first, third, fourth, sixth, seventh, eighth, ninth, and 10th. But these complicated operations are usually not performed when you are dealing with a big vector of observations coming from a vector of random variables or a random vector. You usually perform simple operations like investigation of their mutual covariance, their individual variances, and other such quantities which summarize the unpredictable behavior of this big random vector. You usually do not find the joint PDF, the marginal PDF, and other complicated quantities if you are working with random vectors. The kind of quantities that you do work with when you are working with random vectors are the values of means of individual random variables in a random vector, the second moments, centralized or otherwise, of individual elements in a random vector, and the correlation between two elements in a random vector. These pieces of information can be nicely arranged in the form of vectors and matrices. For example, if you have found the mean values of all elements in a random vector, you can arrange those mean values in the form of another vector. And if you have found the correlation between all possible pairs of elements in a random vector, you can arrange all these values in the form of a matrix. So the entry at 1, 1 location in the correlation matrix will be the correlation of first random variable with itself, which is also the second moment, the regular second moment. Similarly, other diagonal entries will have the second moment of other elements in the random variable. And the off diagonal entities, for example, the entity at 3, 1 will be correlation between the third and first random variables in the random vector, and the entry at 5, 6 and 6, 5 will be the correlation between fifth and sixth element in the random vector. So if you find the second moments and all possible correlation values, you can arrange them in a matrix which is called correlation matrix. Similarly, you can find variances and covariances. If you find variance of a certain random variable in a random vector, that variance goes in the diagonal location. So the variance of first element goes in the 1, 1 location, and variance of fifth element goes in the 5, 5 location, and off diagonal locations will have covariances. The location 3, 1 and 1, 3 will have covariance between first and third element in a random vector. So you form these correlation matrices and covariance matrices, and usually they summarize the relationship between different elements of a random vector. Once you have found correlation matrix or a covariance matrix, then one interesting thing to investigate is that whether this matrix is diagonal or not. If the covariance matrix is diagonal, there are entries only on the principal axis, then this covariance matrix represents a collection of random variables which are not correlated with each other. And this characteristic is useful in pattern classification, the kind of example we saw where we were trying to classify an image into different alphabets of Urdu language. If you have a covariance matrix that is not diagonal, you can transform the underlying random vector into another random vector using a linear transformation in such a way that the new random vector has elements which are not correlated with each other, and the procedure is same. You take the covariance matrix of the original random vector, find its eigenvectors, find its eigenvalues, arrange all the eigenvectors as columns, making sure that all these columns have unit length, and then using this matrix as the linear transformation which transforms the original random observation of random vector into a new observation vector of transformed random variables. The ideas we discussed for a pair of random variables are nicely extended to vectors of random variables. You can have such linear or other non-linear transformations which take a random vector and give you a new random vector. But these transformations are not usually used to find the PDF of the transformed random vector. Actually, most of the time, the PDF of the underlying random vector is also not known, only the summary of their unpredictable behavior as given by the values of mean, variance and other moment is the only thing that is available to us. So if you use a linear or non-linear transformation which takes a random vector and gives you a new random vector, then you can use that to transform a given random vector to a new random vector. One important transformation of this class is the transformation which takes the random vector, all the random variables in the random vector, and sums them together and give you a new random variable. So this transformation is not a linear transformation, it is a simple transformation which takes a random vector and gives you a random variable. It just adds the observed values of all random variables, and that is the value of the new transformed random variable. So if our underlying random vector has individual random variables x1, x2, x3 all the way to x capital N, the new random variable z is simply equal to x1 plus x2 plus x3 and all the way to x capital N. So underlying random experiment gives you n observations. You observe n scalar valued quantities, you add them together and get one scalar valued quantity, and that is the transformation which is very important, very interesting, and it is used very often in statistical analysis of samples, where you have a large population, and from that large population you take a small sample and then you try to see if that sample represents that whole population or not, and what are the relationship between this sample and the whole population. So this is the only transformation that we are going to discuss in some detail. Other transformations, linear or non-linear, which take a random vector and give you another random vector, have their applications in pattern classification and other applied areas of probability theory, but we are going to look at just this transformation where the new transformed random variable is sum of a finite number of other random variables in the random vector. Please note that in some cases the books talk about average of a few random variables. So if you are working with a random vector of say length n, you can talk about a transformation which takes all these random variables in the random vector, adds them together and gives you a new random variable. Or you can add them together and then divide by the number of random variables in the vector, capital N. So in either case, you are doing almost the same thing, because dividing a sum of random variables with a constant number does not change much. So if you are working with sum of a few random variables or average of a few random variables, the procedure is same, the results are almost the same. Let's see why we need to work this problem in greater detail and what is the importance of this problem. Suppose there is a population of individuals and there is a certain quantity of interest that you measure from each individual in the population. So you pick a person from that population randomly and measure that quantity. Certainly, the observed value is a random variable because you are picking the person randomly. If you are picking the person randomly, you cannot predict beforehand what the observed value could be. Example is, the population is all the students in a university, and the quantity of interest that you measure is, after picking a person randomly, the height of that person. There can be other examples, but the point is, if you are making such observations, you must assume that this unpredictable quantity, the height or any other quantity that you are measuring, is following a probability model. It is coming from a PDF. It is following a probability density function, and the value that you pick and observe follows that probability density function. When it follows that probability model and you pick an individual and measure its height, then you are making one observation. You are making one run of that unpredictable experiment where you pick a value. If you want to pick more than one values, then you have some problem. Suppose you pick one person out of the population and measure his height and make that person stand on one side and pick another person. When you have placed the already picked person on the side, you have reduced the population size by 1. You want to do that to avoid repetition. You don't want to pick that person again and measure his height again. That is understandable, but once you remove that person from the population, you change the nature of the population. Now the remaining population cannot be assumed to follow the same PDF, the same probability model as the whole population. But we usually assume that population is huge. Population is so large that if you make one person stand on the side, the remaining population almost behaves in the same way of the whole population. So you make the first person stand on the side, you pick the second person randomly, measure his height. So this observation is coming from another random variable, because you have changed the nature of the population, the nature of the PDF, the nature of the probability model has changed. The second observation is observation of a second random variable. And if you make the second person stand with the first person and pick a third person, this third observation is coming from another new random variable, the third random variable. And suppose you pick a finite number of people, say 10, 20, 25, out of a big population, then as you keep on picking persons and making them stand on the side so that you don't pick that person again, you are changing the population, you are reducing the size of the population by 1, and as the size of the population gets reduced, it follows a new PDF, a new probability model with each reduction in size. So your observations, which you can call small x1, small x2, all the way to small x25, are coming from different random variables, capital X1, capital X2, all the way to capital X25. Now, you don't know anything about the behavior of the population as modeled with the probability model. You don't know anything about the PDF of the probability model that is governing the heights of the people that you have picked. But you have 25 samples, or 10 or 20. You have a finite number of samples. Looking at those samples and looking at the finite number of measurements that you have made, can you make a guess about different parameters of the whole population? For example, by measuring the mean value of observed heights, can you make a guess about the mean value of the whole population? The mean value as obtained by integration of the PDF multiplied with the value of the parameter. So if x is the height, then integration of x into PDF of that random variable x gives you the mean value of the whole population as modeled by the probability model governing that PDF. So that is the true mean of the population. Here you have 10, 20 or 25 observations and you take average of that. This mean value of the sample, has this any relationship with the mean value of the whole population? Then there is the variance of the whole population. Looking at the number of people in the sample, the mean value of this sample and the variance of this finite sample, can you make a relationship between these quantities, mean, sample size and variance, with the variance of the population? These are the kind of questions that are answered by taking this transformed random variable z, where z is sum of a finite number of random variables or average value of a finite number of random variables. This is an important transformation and we are going to see if we can find the PDF of this transformed random variable z, where z is sum of a finite number of individual random variables. For cases like this, it is usually assumed that the population is huge. It is very large compared to the sample that we picked. So when we removed a few individuals from the population to form our sample, the remaining population is so large, almost as large as the original population, that remaining population has the same probability model. So as you keep on picking individuals and making them stand on the size, the probability model does not change, the PDF does not change, and the observations that you make, even without replacement, even with keeping your observed values on the side, are coming from the same probability model, the same PDF. In this case, these observations are said to be coming from independent and identically distributed random variables, usually called IID random variables. So they are independent because you are picking the individuals independent of each other. You are randomly picking. If you have picked a tall individual, you do not search in the population for another tall individual to be picked. You pick the next person randomly. Similarly, if you have picked a short person, you do not try to pick a short person to make your average value small, and you do not try to pick a tall person to compensate for the previously picked short person. You always pick the next person randomly. So if you are picking them randomly, then the observations are independent of each other. And if the population is large, then all these observations are realizations of random variables that are identically distributed. So in cases like this, usually we assume that the observations are distributed in identical and independent manner. So if we have a transformed random variable z, which is obtained from sum of a finite number of independent and identically distributed random variables, we can find the PDF of this transformed random variable from the PDF of any one of those random variables which got added together to make z. If x1, x2, x3 all the way up to xn are identically distributed, then we can say that their distribution is same as another random variable x. This random variable x is representing all of these random variables x1, x2, xn in the collection. So this random variable x has a PDF which is the same as the PDF of all the random variables in that collection. So we want to find the PDF of random variable z from the PDF of random variable x, because this PDF of random variable x is PDF of all of the random variables that get added together to form z. We can easily do that, and if they are independent, then there is a nice relationship between the PDF of x for all the x's and the PDF of derived random variable z, which is obtained through summing of all these random variables in the collection, or through averaging, which is summing followed by dividing with the number of random variables in the collection. We will undertake this investigation in next lecture. What we learned in today's lecture is transformation of pair of random variables in such a way that the underlying pair is correlated but the transformed pair is uncorrelated. Then we started discussion of vectors of random variables, and we said that all the ideas of transformation of random variables, the joint PDFs, the marginal PDFs, the joint CDF, the marginal CDFs are applicable to vector random variables. If a random vector gets transformed to a new random vector, we can even find the joint PDF of the new vector if we know the PDF of original vector and the functions that transform the original random vector to a new random vector. But we usually do not do such complicated things because we don't need them. The only thing that we are going to investigate in detail is the PDF of a scalar valued derived random variable z, which is obtained by adding the observed values of all the elements in the random vector. This we are going to do in the next lecture. Till then, I wish you the best. Thank you. Khuda Hafiz.